talking about bidirected infinite state systems, when I talk about a class of systems, it usually means we're interested in reachability in that class of systems. And so, as we all know, the reachability problem is can you reach a configuration C2 from a configuration C1? And the problem is, it's a difficult problem. So both conceptually and computationally, right? We know that in VAS, reachability and Ackermann hard, and it requires complicated techniques to solve this problem. And in recent years, we've been working on a restriction of general infinite state systems, namely bidirectedness, where essentially for every transition in the system that you have, you also have an opposite transition that goes in the opposite direction and has the opposite effect. So let's see a few types of systems where this makes sense. So you can have a pushdown automaton where you have push action. So let's say an A means you push A onto the stack, and an A bar means you pop A from the stack, and you have configurations in states and stack contents. And then it makes sense to say something is bidirected because whenever there's a push, there's a corresponding pop in the other direction, and vice versa. For encounters, or in other words, VAS, you can interpret the A as an increment to counter A, and you interpret the A bar as a decrement, and then again you can say what it means to be bidirected. Here you have configurations in natural numbers, and you can do the same thing with Z counters. Bidirectedness makes sense as well. So bidirected means for every transition, there's an opposite transition. And the interesting fact about this restriction is that it has been studied by three pretty different communities. On the one hand, it's been looked at, I don't know if you can call this the infinite state systems community, but it's maybe closest to the people here, bidirected VAS, and their connection to finitely presented commutative semigroups. So this has been studied a lot in the 80s and 90s by Ernst Mayr, Albert Mayr, and Ulla Kopenhagen. And they showed really nice things about these systems. And then completely separately, I think there has been no interaction between these two communities by people in static analysis. They want to decide properties about code. And they looked at this as, in terms of pointer analysis. You're given some set of pointer instructions and you want to know, is it ever possible that this pointer points to this particular variable? And they also have some really nice ideas. And it's also been looked at in group theory. So there's this concept of Stallings automata developed already in the 80s that you can use to represent subgroups of group. We have air conditioning. At most one of the two. Okay. So Stallings automata are a super prominent technique in group theory. When you want to compute something called subgroups, you usually represent them using a type of bidirected automata. There's a slight variant called dual automata that is that's not quite as restricted as Stallings automata and also has algorithmic advantages. In bidirectedness, they're also called involutive. So there's several terms that describe this idea. And yeah, surprisingly, there's been very little interaction between these two. Yeah.
What about reversible computations?
That's actually something different. I wanted to get to that now. Right, so you might ask yourself, why am I not calling this reversible? Because when I saw these papers on static analysis, I thought, well, let me explain this to you. Actually, this is called reversible. And then we start working on this, and we start writing the paper, and I wanted to, in the preliminaries, I wanted to say, this is called reversible. And I wanted to add a reference to the first paper that calls this reversible. But actually, there's no paper that does this. For some reason, we all think this should be called reversible. But in the literature, it's never really been called reversible. There's this one occurrence in the Meyer paper that says that the word problem in commutative semigroups is equivalent to reversible vector replacement systems. And they cite the Hack paper from 1974. But then, okay, then I thought, okay, I'll cite that. But then Hack never calls it reversible. He calls it symmetric. So then there was nothing to cite as the paper that introduces the concept as reversible. There is Jérôme Leroux's paper on reversible reachability, but actually he switched terminology and now it's mutual reachability. So that's also not what we mean. And instead, there's a very well-established term in dynamical systems called reversibility, but it means something very different. It means that there exists another system whose step relation is exactly the reverse. So for VAS, that's trivially always the case. You can just always take the system, reverse all the edges, and you have another VAS. So in that sense, all VAS are reversible. Right? For them, it's about preserving information. So I think reversible is really not the right term.
Maybe symmetric then.
Yeah, okay. Symmetric would be a candidate. The problem with symmetric is there are many possible symmetries that you could have in a system, right? And saying symmetric, and as if that were the only possible symmetry that you could have, right? Like you could have symmetries by having permutations on the states and not just reversing edges. I think symmetry is too vague of a term.
But is there any computation model which is not reversible according to this definition?
So usually
machines are reversible.
Okay, so I should say what they call reversible is there has to be another system that's the reverse, but in the same class of systems. So you allow a certain set of possible maps that are admissible, and then a particular system is reversible if there's another system in the class that uses this within the same class of admissible operations. So within the class of VAS, every VAS is reversible. Right, but instead there's this well-established line of work with many papers that calls this bidirected, and so I think bidirected is a good term to use. I mean, there's the other usage of involutive, but I only discovered this after really started working on this. I think bidirected is, yeah, that's what we chose. All right, so what am I going to talk about? So first of all, I'll talk about bidirected VAS. That's really old stuff. And I'll mainly talk about this to give you an intuition of the relationship to other areas of math. Because I'll explain the connection to polynomial ideals. And so you can see this both as like some explanations of some ideas, but also as motivation. Then the case of groups. So this is another connection to pure math. This is also, you can also see this as motivation, but it's also tricks that show up later. Then I'll talk about bidirected integer VAS, push-down integer VAS, and then there will be a broader picture result that generalizes the results I mentioned before. And this will be about the complexity of bidirected reachability compared to other systems where we already know decidable reachability. So basically, it says the complexity almost always goes down. And finally, I'll talk about push-down VAS, where general reachability is not known to be decidable, but in the bidirected case, it is. All right. So let's see. Yeah.
Especially, have you ever approached someone asking a question about reachability, but not between a single configuration, but some sets? Like we are defining a set called families of sets of configurations, and then we are saying that bireachability holds if from one set I can go to another, then I can also go in the opposite direction. It's not clear if it's like from every configuration in this particular set I should go to some configuration in the other one, or if there exists a connection, but this kind of
so instead of existential sentences, you have higher quantifier alternations in the configuration.
But it's like you don't consider bireachability, you consider bidirected systems, right? So this is
right, yeah,
so
exactly. So these are two different
then
things.
it's clear, right?
You can take an ordinary system and look at the mutual reachability relation, where you have the relation if you can go both ways. But that's very different in some cases than this structural restriction, where you require that between any, there's always a reverse edge. So as I've just learned during breakfast, in pushdown gas, for example, the mutual reachability is the same, is as hard as general reachability. So I think Jerome and Roland and Wojtek and Ehren have discovered this independently. And I just learned. Yeah, but the bidirect reachability is not to be decided. All right, so in a VAS, so you all know what a VAS is, I don't need to explain this. And it's bidirected, as we said, if for every edge there's a reverse edge. Or does anyone want more explanation on what a VAS is? Right, and so the nice result is that in bidirected VAS, reachability is exponential space complete. And their motivation, though, was what is called the uniform word problem in finitely presented commutative semigroups. So let's first describe the connection between the two. This is super simple. So a presentation of a commutative semigroup is just a finite set of pairs, or a presentation, you could also say it's not finite, but let's restrict to finite sets. Just a set of pairs of vectors. And this induces a congruence relation, which is just the smallest congruence relation that contains this finite set. So it means it's the smallest reflexive, symmetric, transitive relation, so that whenever you have a pair, you can also apply it in larger vectors. You can always replace u by v. So this is you could also see this as a bidirected Petrinet. So in other words, you are in this relation. If you can obtain u from repeatedly choosing some should be x, you can get from x to y by repeatedly choosing these pairs. So now the uniform word problem is you're given a presentation and you want to know if two vectors are equivalent. And this is called a uniform word problem because the word problem for a semigroup is you're given two descriptions of elements and you want to know do they represent the same element. And this is called uniform because the description of the whole semigroup is part of the input. Right? This set of pairs describes your semigroup, and uniform means it's a uniform algorithm for all the semigroups. Right, and so this is super simple. Reachability, bidirected VAS, interreducible. This is the same way as you go from a VAS to a Petrinet and back. So you just add two more dimensions, and then you have it's this simple trick where you encode the state into more counters.
Could you explain this a bit?
Oh, I see.
More?
So right. So if you take a bidirected VAS, so if you want to do this trick in VAS, you have to add 3 extra counters because you're using VAS semantics. But here we're using the semigroup, or actually Petrinet semantics, and then 2 extra counters suffice. So what you do is, if you want to encode n different counters, you represent the counter I by I, comma, n minus I. And then in your step relation, you always say, if you want to say you go from state I to the state j, then it means you first have to subtract I and n minus I, and then you add j, comma, n minus j, and then there's only, you always have to.
So, but if in a simple setting, when you don't have states,
yeah.
How do you represent a transition by, like, you add a vector v in this uniform word problem? So I'm just lacking some.
Each letter is a count.
This problem is literally Petrinet reachability.
So that presentation link is exactly the set of your VAS transitions.
Yeah, so the semigroup presentation is just, you can think of it as a Petrinet. You subtract a vector and you add a vector. Right? This relation says, if you have u and v in your set of pairs, then you can go from u plus w to v plus w, which means you replace you subtract u and add v. And so you can think of it as a Petrinet. And since it's symmetric, it's then equivalent to the algebraic structure. Commutative sense. Right. Does this make sense? All right. So how did they show this? They encode the problem. They discover that you can encode the reachability problem in a polynomial ideal. And this is a super nice ideal. So an ideal in the context of polynomial rings. This is not the same as ideals in WQO, which maybe more people here are familiar with. So in a polynomial ring, so here we're considering polynomial rings with rational coefficients. The whole thing also works with integer coefficients, but the fact that it works with rational is even more interesting. So an ideal is a non-empty subset, so that on the one hand it's a group under addition. So if you take two polynomials in the ideal, their sum is also in there, and if you the negation is always also in the center. And it's closed under multiplication with any other polynomial. So if you take something in the ideal and you take any other polynomial and you multiply them, you're still in the ideal. And ideal are really the central concept in the structure theory of rings, right? This is if you want to build rings, you always take a ring and do mod by an ideal. It's the first thing you learn about a ring. Right, and so if you have some subset of polynomials, you can also always look at the ideal generated by that subset.
The minus f is like implied by multiplication, right?
Sorry?
It's minus f.
Ah,
So
right,
there's
good point.
kind of
Yes. So how do you translate bidirected reachability to or the uniform word problem to membership in ideals? So the idea, what you do is the following: you encode a vector. So for every vector, you can define a monomial, which is you take these the variables and you take the individual components as powers to their respective of their respective variables. And then this finite set of pairs is translated into a set of polynomials, namely you just subtract, I think, yeah, this should be v minus u, but it doesn't really matter. We can assume that the set p is symmetric. Is symmetric. So you just take differences of these monomials. And then you can actually show that two vectors are reachable from each other if and only if the corresponding difference polynomial belongs to the ideal. So it means to decide reachability, you just compute, you take this ideal and you check, is it in this ideal? And this is a well understood problem. This membership problem is expressed completely. But as you may notice, this is 7 years later than the result on VAS. And what's interesting here is this result actually uses a lot of the ideas in the paper on bidirected VAS. So it was first known that if the ideals have this special form, then you can do it in exponential space. And it actually uses a lot of VAS techniques. So I think VAS also contributed to this theory of ideals here. But I'm still citing the more general thing because this is what you should keep in mind, that if you have any finitely generated, any ideal given by finitely being generators, then you can decide membership in exponential space. And I thought it would be nice to see how this is shown. All right, so one direction is easy. If you can go from y to z, then the difference polynomial is in the ideal. That's just really direct. For members of P, of course, by definition, and to simulate a single step relation, if you do a step and you apply it with in the context of some added w, then you can write this difference polynomial as just this polynomial that you have in there by construction, and you multiply this one polynomial, which you can do because it's an ideal. Because you can always multiply arbitrary ideals. You multiply this polynomial. Okay? And then it's also you can also do transitivity. So if you can go from u to v, you can go from v to w. You just take the difference between the two polynomials you know are in your ideal, and then what you get is the step directly from u to w. Right, and then symmetry, of course, also because you can negate. All right, this is easy. The interesting direction is that multiplying all these general polynomials doesn't give you anything more than the reachability relation. That's the more interesting fact. So let's see why that is. Now suppose you have this binomial ideal. So if you have just a difference of two monomials, that's called the binomial polynomial, or just a binomial. Suppose we're in this ideal, then that means it can be written as a linear combination of the generator polynomials multiplied by some polynomials, right? You can see that everything you can write this way is an ideal, and so that means the elements that can be written exactly in this way, that's exactly the ideal. So being in that ideal means your difference can be written like this. So now the g's can be polynomials over q. So first we multiply by some common denominator. And then that means what we can actually write is k times x to the z minus k times x to the y as some linear combination. And we can also assume that all these factors here are just monomials, right? Because if the g is a sum, then you just split that apart into more terms. And we can also assume that all the coefficients are just 1, because if it's a positive number, then you split it even more into more terms. And if it's negative, then you just flip the two exponents. Right, so we not always write it this way. And now it's a simple observation, actually. So first, you assume that y and z are different, otherwise it's true. But then, this monomial x to the y somewhere has to appear among the negatively occurring powers. Right? Otherwise, if this monomial didn't occur, there would be no way it can occur here. So that means you can write x to the y as some ur times wr. And that means you can bring over the corresponding difference, you bring it over, right? You have two that cancel out, and you bring the rest over. So the x to the vr plus wr, that's what does not cancel, and you move it over. Okay, does that make sense? So now we write it this way, and now one of two things can happen. Either the vr plus w, so first of all, we know that this vr plus wr must be reachable from the y, because we chose it because it appeared in one of these pairs, right? So it's reachable in one step from the y. So either this is already z, and then we're done. Then we have shown that you can reach z from y. But in the other case, we can just continue. Now we have another term here that we know must appear on the side, so it has to match somewhere, and then we can bring the other one over. Then this disappears, and we get the other one, and so we get more and more terms, and for all of them we know that they're reachable from the y. And at some point, either the right-hand side becomes empty, then it's a contradiction, or we reach z. All right. So that's a really nice connection. We know that bidirected VAS correspond to a natural object in mathematics, finitely presented commutative semigroups, and they're also connected to polynomial ideas. And this connection to polynomial ideas has been explored more by Meyer and Kopenhagen. So from this connection, they extract descriptions of the reachability sets using polynomial ideal techniques, and so on. So let's see how these three areas benefited from each other. On the one hand, the complexity upper bounds actually go both ways. So the complexity upper bound for exponential space. So first of all, what Meyer and Meyer do in the 82 paper is they first use this ideal membership characterization to be able to apply determinants and solutions of linear equation systems, right? Because membership in an ideal is solving the linear equation systems in a ring. And actually this ring is a domain, so it embeds in a field, the field of rational functions. And so they can apply techniques about fields, and that way get a doubly exponential degree bound. So they show that if there is a solution, then there's a solution with doubly exponential degrees. And then it's just, and from that point on, it's just linear equations. But doubly exponential degrees still doesn't give you exponential space, because then they reinterpret it as a VAS, and then you know, as you saw in the proof, if the maximal degree in your representation is at most doubly exponential, then that means the number of steps is at most doubly exponential. And then you know by binary encoding you can represent the states in exponential space. So you also need VAS to get the result on binomial polynomial ideals. And they used VAS, on the other hand, to supply the other two areas with lower bounds. So the lower bound for bidirected VAS is just a slight variation of the Lipton technique, and so that gives you an exponential space lower bound for polynomial ideals. So I think this is super fruitful connection. All right. Any questions? Yeah?
What is happening if on the bus side you would try to take continuous semantics? Does it correspond to any kind of object in math?
I have no idea. Good question. I don't know. Yeah, we should look at this. All right, how are we doing on time? Half an hour, okay, that's good. So there's also a connection to groups in the following sense. You can look at automata where the edges are labeled by elements of a group. And then we can build configurations which are pairs of states and group elements. And you go one step by just multiplying the element on the edge. That's the natural thing you would do. And then you can call this automaton bidirected if for every edge you have a reverse edge. And this is connected to finitely generated subgroups. And a finitely generated subgroup is just the smallest subgroup of the group that contains this finite set of elements. So you take all the products, but also including the inverses. And the subgroup membership problem is given elements G and G1 to Gn, and you want to know does G belong to the subgroup generated by these elements. And now the connection is that reachability for bidirected automata is even deterministic log space interreducible with the subgroup membership problem. So the connection between the two is I don't know who first invented this. You can claim it's Benoit in the 60s, or no, maybe not really, but maybe Stallings. And we observed you can even do it in log space, but this is not a big thing. So it's simple observation. That's what I want to talk about here. And this is mainly to get you to see this connection to subgroups, because it's not obvious, right? Because if you have an automaton, you might think there's so many different ways of building paths. How can this be connected to just having finitely many generators in a subgroup? That's the interesting part. So one direction is obvious. If you have a subgroup, then of course you can construct a bidirected automaton. You just do the obvious thing. You have one edge for the positive, one edge for the inverse, and then of course everything you can generate is exactly the same. The more interesting thing is the converse. So suppose we have a bidirected automaton, and we want to know, can we reach from P1 to QG? Of course, the first one is different than the simple reduction. So let's assume the first one's 1. So the first step in the reduction is to make sure that the final state is the same as the first. We can assume that. And for that, you just pick an arbitrary path from P to Q and look at its effect. H. So that's the group element spelled by that path. And then you can observe that you can go from P1 to QG if and only if from P1 to P itself you can go to G multiplied by H to the minus 1. Right? That's obvious. If you can do this, then of course you can do the path in reverse and multiply the H to the minus 1. And conversely, if you can do that, you can also do this. You can have the path here and then also get this. So you can already see the cyclic case is the general case. So in the sense that the final state is the same. And the second step is the following. Now for every state that's not the initial state, you pick some path from P to R. And let delta R be its effect. So just the element that's spelled on its path. You do the same for P itself, and then you choose the identity element. Now you picked all these group elements, and now you construct a generating set. And it's always follow the path, it consists of one element for every edge. First you go to R with your favorite effect, the effect of your favorite path. then you apply H, and then you go back the other way. So clearly, right, the obvious claim is you get exactly what you get in the entire automaton. So one direction is obvious. Of course, all of these paths that we constructed are loops. So everything you can get in this group are obviously even paths in our automaton. But the converse is true as well, because you can piece together every run by these elements. So suppose you have some run consisting that reads H1, H2 up to Hn, and it reads our target element G. Then you do the obvious, construct the obvious path. You just take all the paths that correspond to the edges on your path. Right? All of them belong to F. But then if you look at the product, these backwards and forwards paths, they always cancel out. Right? And so what you get in the end, so this one is the identity by choice. These two cancel out, then these two cancel out, and then you get exactly this G. Okay. Good. So bidirected automata are a classic tool in algorithmic group theory, most prominently known as Stallings automata. And there's many different results that came from this connection. So for example, there's the connection from bidirected automata to finally generated groups. So this is a somewhat not so well-known fact. There's a result by Benoit from 1969 that shows if you have a general automata, not necessarily bidirected, over a free group, then you can decide reachability there by a simple saturation algorithm. And it's the saturation algorithm we now know for push-down automata. But she first came up with it for free groups. And so this was kind of an application of automata to finally generated groups. And the same idea was then reinvented by Stallings in Stallings automata. But there are differences between the two notions, but the idea of this saturation technique is essentially the same. So on the one hand, automata have been useful in groups, but on the other hand, in this research project on bidirected automata, groups have also supplied lower bounds. So for example, to show p-hardness of bidirected push-down automata, you can use the known fact that subgroup membership in free groups is known to be p-hard. So this was surprisingly hard to get because so just p-hardness of PDA reachability, the typical techniques using circuit evaluation, it doesn't work at all. Because the PDAs you get, they're necessarily very non-deterministic, because basically you guess the path of your polynomial time computation with a lot of non-determinism and backwards. And you only make sure that in the end everything worked if you guess correctly. And if you want to do this for bidirected, you have to do very different things. And one of the two proofs we have is via free groups, so from group theory. And the other one is if you have a bidirected push-down automaton but with two stacks, then undecidability is not easy to show. And this you can also do from the fact that Mihailova in the 70s has shown that the subgroup membership problem is undecidable in a direct product of two free groups. And this uses deep stuff from group theory. And so this is one way to use group theory in the other direction.
Sorry, Georg, so like two push-down automata, they are like the same like Turing machines, right? So are you saying that undecidability in bidirected Turing machines is not easy to show, or is something else maybe?
I think this equivalence between Turing machine and two-stack automata, I'm not sure if this translation survives bidirectedness.
I see.
Right? I think the translation can get destroyed in this. So I think it's different from I think if you just have bidirected Turing machines, undecidability is not difficult, right? Because there's this trick that if you have a deterministic system, you can always make it bidirected. We talked about this at some point. That if you add back edges, you don't destroy anything because all you can do is go back, but eventually you have to go forward again. So I think for Turing machines, that's much easier. But yeah, for this, we use.
If instead of two push-down automata, you consider two counter automata with zero tests, is it Is it
That's a
then
good question.
like what about bidirected to counter automata?
Well, that's a good question. I don't know. Very good question. Yeah. Right. Good. Okay. So that's all I had about groups. Groups. So now let's look at integer class. And now, if you know integer class, you might think, well, that's a group. That's actually the same as groups, and that's true. But I wanted to show a different technique. So a d-dimensional z-VAS is just a VAS where you allow yourself to become negative. So configuration is a pair of a state and a vector, but now it's only integers. But the machine looks the same. And again, the transition relation is this, and bidirected this is as we know. And if you look at general z-VAS, then the reachability problem is NP complete. And the interesting thing is that if you do this bidirected, then you can do it in polynomial time. And one possible proof is to use the technique we just saw. You reduce it to subgroup membership. And membership in a subgroup is just solving a system of linear equalities. Right? So a vector is in this a group generated by a vectors v1 to the n, if and only if you write the linear equation system. So the number of times you use each vector is a coefficient when you reduce this to solvability. And this is in polynomial time.
I will interrupt because this always gets me confused. It's good to say that these are equations using p, while these kind of inequalities will be NP complete, these integer inequalities.
Exactly, yes. The point is it's equations. So two things, you have to have two things. On the one hand, the solutions have to be over the entire integers, not just the natural numbers. And you only have to have equations. Yes, good point, yes. If you have these two things, then you're in polynomial time. But I want to mention a slightly different proof, because the technique will be useful. So as I said, we use the fact that the ILD problem, integer linear diagonal type equations. So you're given a matrix and a vector B, and you want to know is there a vector X so that the equation holds. That's solvable in polynomial time. That's what we're using.
Sorry, Georg, so coming to this p time results,
Yeah.
Why this is in p time? Is it some deep
It's
result?
not so easy to see. So this is it's a somewhat non-trivial result. It's
not that, but I'm saying two slides back. But yeah.
So
you
one way
were
of
just
doing this
proving
is using equations. So the first proof I just showed you, you can reduce the reachability problem to membership in subgroups, and that is the same as solving equations.
Okay, but why solving equations is in P? Is it easy to see?
That's this result.
Okay,
that's a non-trivial
you're
result.
just I see.
Yeah.
Okay.
So basically, it's Gauss elimination, but using rings and modulo condition. And you have to very carefully track how large all the determinants get. It's very technical, but this is a well-established thing. So here's a different approach of doing it, not the subgroup way, but more but closer to techniques we know from infinite state systems. The idea is so instead of, it's kind of a dual approach. So the approach before constructs a generating set of all the possible elements that you can reach. Here, we're directly constructing a set of equations that describe when something is reachable. So instead of generators, we have equations. And it's very similar to what all of you would do to solve z-VAS reachability. Namely, you do a flow condition. So, we take a vector where every entry describes how many times we take an edge. And since we're bidirected, we can allow ourselves negative numbers, right? Having a negative number just means you have to take the edge backwards. And so if we can write down a set of equations so that every solution corresponds to a run, then we're done. We can solve reachability because then you can impose additional restrictions that say, oh, I reached exactly this configuration that I want. Okay, so that's all we have to do. And the idea is you take a flow condition, which says that for every state Q, the number of edges that go into Q is the same as the number of edges that go out of Q. And if you want to have a flow that goes from state S to T, you have two exceptions. If Q happens to be S, then you allow yourself one less incoming edge, so you add one here, and for T, smash it. And now for general ZVAS, you would have to add some more conditions. You would have to say every edge is used a non-negative number of times. And the other thing you have to impose is that all the edges you use are a connected set of edges. Right? Otherwise you have a solution. So every cycle is a flow. And so if you were to just write this, then you could have two completely disconnected cycles, and this would of course not be right. So usually if you want to do ZVAS, you have to have this connectedness condition. And there are nice ways of expressing this. These are all ideas by these people. But here we can do without this. We can do with just with equations and integer numbers. So I'm claiming that whenever we satisfy this, then there's already a run. And here's how you show this. So suppose we have a solution. So this is our bidirected ZVAS. I'm not drawing the back edges. And since we only want to understand how many times you take each edge, there are no effects on the edges, right? We just want to count how many times you use an edge. So now suppose this is our vector. It says this edge is taken once. This edge, so this edge is taken -1 times. And this edge is taken once. Now we argue as follows. First we pick a spanning tree. And then we just do what we need to do to execute these edges. And in between, we walk on the spanning tree. So our first goal is to execute this edge. So that means we start in S, and we go up in the spanning tree. So the fat ones are the spanning tree. And then we can already execute this, right? Then we can do this edge. Then our next goal is this, but we want to execute it negatively, so we want to go up. So that means we go this negatively, so minus this edge. Then we go here in the spanning tree, so minus this edge. Then we go to the right, so plus this edge, and then we finally can execute this edge. Right, and then we do the same for the third one. You always do what you need to do.
Yeah.
So now, look at what we did. Now, if you look at all of these together, then that's an ST flow just because it's a path. Right? Every path satisfies the ST flow condition. But by assumption, the blue part is also an ST flow. That means the difference, the red stuff, is a flow. So flow meaning with no exceptions. And it's a flow that's contained in a spanning tree. But now, if you're a flow that's contained in a spanning tree, you can argue that actually it must evaluate every edge by 0. That's a simple argument. If you walk inside a tree, and you consider an edge that just points to a leaf node, that means you have to go down the edge as many times as you go up. So that has to be 0. And then by induction, everything has to be 0. So that means, actually this red part is 0 everywhere. So this path that we constructed here has exactly the same valuation as the blue part. So then, any more questions? Okay. So yeah, I showed you this because this will be useful in the next type of system. So now we look at slightly more complicated systems, which are push-down integer paths. So here we have a push-down and integer counters. So our automata have 3 types of edges. You can add vectors, you can push symbols from the stack alphabet, and you can pop symbols from the stack alphabet. Configurations consist of both a stack and some counter values. And that's it. And the result I want to talk about is that in these systems, reachability is still p-complete. And this is even more surprising than just the ZVAS setting, because even in dimension 1, push-down integer vast reachability is NP-complete. But here, even in arbitrary dimension, we're still in normal time. Right, in dimension 1, this is easy. You can easily reduce subsets on. All right. And in the general case, the idea is again similar as for the as in the ZVAS setting I just described. You formulate a flow condition, but in a grammar. This is an idea basically due to Javier Esparza, who first phrased this as the reachability problem in BPP nets, communication-free nets. And he showed that if you have these flow conditions and connectedness conditions, that then you always have, then this is sufficient to guarantee the existence of a run. Now the challenge here is to do bidirected reachability, but on grammars. So you have to find a notion of grammars that, and the right set of symmetry conditions that are, on the one hand, true, but also enough to get this technique going of just imposing equalities. And this is what we do here. So you translate this into a notion of bidirected grammars, and then you show that the flow condition is again right, and then you get again the system of linear equalities. So how does this work? So let me first show you how to construct the grammar, then we'll observe the symmetry conditions. So first you introduce non-terminals for pairs of states, and then you do the standard translation into a grammar. For every edge, you add a production that allows you to directly produce a vector. I think it's most natural to have terminals be integer vectors. And then for every state, you say to go from P to Q, you can also go from P to R and then from R to Q. So everything, whatever you can do from P to R and everything you can do from R to Q, if you put them together, you get something producible by PQ. That's natural. And to simulate pushes, whenever you have a push instruction that goes to R from P, and you have a pop operation that goes back from S to Q, then you know that everything you can derive using RS, you can also derive from PQ, right? Just by doing push thing, do your thing in between, and then go back in that. So this grammar does exactly what we want. Right, yes. And this is the thing you're allowed to add because you're bidirected. Because since you're bidirected, this doesn't add anything. So what the sense is, going from P, so everything you can do from P to Q, then back from Q to P, and then from P to Q again, is also allowable by PQ. And this you're only allowed because you're bidirected. So let's observe what symmetries we have here. So now we have this flip operation, which we denote by a bar. We say a grammar is bidirected if there is an involution. So this is an involution, meaning if you apply it twice, you're back where you were. And you know that for every production, you have this inverse production, which is just the flipped version. Also, for every production, you have one. If you flip the left-hand side and you flip the terminal, and then you also have these triple productions where you can go back, then so you go forth, then go back, and then go forth again. Okay. So you can observe these three things, and it turns out if you have these conditions, then you can again play this trick of just imposing equalities. So let's see how to do this. Just for notation, whenever we now have a sequence, we say the bar version of it is just the obvious thing. You just reverse and flip all the letters. So now we want to write down equations that say when a certain element can be derived. And we use exactly the same idea. So first of all, we assume that the entire thing is connected. So for every non-terminal, you can reach it from the start symbol. So every non-terminal can appear at a derivation starting from the start symbol. And from every symbol you can derive a point. Everything else you can just go away. And now you introduce a variable for every production. And then you have a flow condition. It just says for every non-terminal A, the number of times you remove it, if you apply the production standard times, is the same number you produce it. Right? Except for the start symbol, you can remove it one too many times, or once more. Okay, now I'm claiming this is enough to guarantee the existence of a derivation.
And these symbols are the W in bar A is the number of occurrences of A in W.
Oh yeah, sorry, I should have said this, yes. So you look at this production on the right-hand side, and then if you have production, you don't care what's on the left-hand side. If you use it xp times, then you multiply with the number of occurrences of A on the right-hand side. So that's the number of times, how many times you produce A. Yeah, thank you. So one direction is trivial. Every derivation, of course, yields a solution, right? You just say how many times do I use this production, it will be a solution. For the converse, that's more interesting, especially because now you can have productions that occur negatively, which is much more natural in the automaton version, but here this is more finicky. So first of all, so let's view this vector. So this vector can be seen as a collection of productions, for each of them we say either it occurs positively or it occurs negatively. Right? And so this is a list of all the productions, and we keep in mind each of them is either used positively or negatively. So we unroll all the multiplicities basically. So now for every occurrence of such a production, we know by assumption there exists a derivation that produces AI. So AI occurs in this word UI. Now what we can do is using our triple production that can, so you can view this, by the way, as adding an occurrence of S bar and S. So you apply this again and again, then you get S, and then a bunch of repetitions of S bar S, S bar S, S bar S. And then from each S bar S, you apply both versions of this derivation, right? Because we had this symmetry that you always, for every production, you also have a negative version. Now you take the whole derivation tree and flip all of them, and then you get all of these words here, right? So you, for the left hand, so you take this derivation, take it positively once, apply it to the S, and then you flip the whole tree and apply it to the S bar. That's how you get this word. Okay? And now this has so many occurrences of everything that now we can apply everything we need. So this kind of corresponds to these red parts in the integer VAS version, right? You just add a bunch of stuff that allows you to just apply everything, and then since everything's balanced, it will work out in the end. So that's what we do now. If you take a positive occurrence, you can apply it as it is to UI, because AI occurs in UI. If you have a negative occurrence, you apply it to UI bar. Right? You just apply it. That's all we need. And now you can observe that in the new word that we have, all the occurrences are balanced. Because what we applied satisfied the flow condition. And also we have one more occurrence of the S here. So then everything evens out. So that means all the way in the end, we can now have, we have all these pairs of A and A bar. And since we know that from A we can derive something, we know from A bar we can derive the same thing but negative, and that's what we do in the end. We just get rid of all these pairs. And then we get a derivation of our element. So you will notice that I lied a little bit, because the derivation that we get in the end does not have the same vector, right? We have a bunch more occurrences, but the key thing is the terminal vector that's produced in the end, that's the same. So we're correct up to the vector we generate. So every vector that can be generated, it has a solution, and every solution gives rise to a vector that is actually that can actually be generated.
And we use this special production S going to S bar S only for the initial non-terminal.
Yeah.
Because in the grammar you assume this as a property of every.
Right. Just because it's nice.
But you didn't need for the
Right.
others.
Yeah. All right. I think this might be a good point to end for this session.
Well, from our side, the tradition of asking questions during the talk, but maybe other people have questions. So are there more questions before we go?
It is there at the end of now. There is this result in complexity theory that symmetric log space equals log space.
Yeah.
And this uses very different techniques, obviously. But do you think there's any connection or any techniques that we've borrowed?
We use it all the time.
Oh.
So we use it. Yeah, I kind of glossed over this. So in this reduction, yeah, I should have attributed Uma Reingold for this. In the fact that you have that this is a log space reduction. You need to compute a spanning. Oh, actually, yeah, you need to compute all these paths. Right, to compute this generating set, you need to compute a path from P to R. And for that you use the Reingold result, because you list all the edges, and then for each edge you decide if you take it into your path, and you do it if and only if you could not have reached your state with the edges you already saw before. And that we already, I didn't go into the complexity.
Other question? Quick one. So if I'm not mistaken, you published a paper that shows that continuous reachability and continuous push down VAS is next time complete.
Yeah.
What about bidirected reachability? Is there something like this?
I think Bala has thought about this, and I think he knows how to solve it.
Okay.
But I don't remember what the complexity is.
But it would be below next time.
Yeah, it's better. I think he may even. I think it was P space or NP, one of the two. But I don't know. Yeah.
Yes, I have a question. So you provide the weight for deciding the reachability problem. Can you
provide
the
what?
reachability relation? I mean, the set of possible configurations that you can reach.
Yeah.
Is it possible to compute it and
In which model? In which model?
I mean, rather than deciding from a state P to a state P, we have to know the set of vectors that we can reach.
Yeah.
P. So the set should be a lattice or something like that.
Yeah, it's even a subgroup.
Even a subgroup. Do you think it's possible to compute in polynomial time? Generator?
Yeah, this is what this construction does. You compute a set of generators. And I think that's the best you can get for a subgroup. I think that's the standard representation of a subgroup, and from that you can. Not sure if there are others that would be more natural. But yeah, that gives you the answer. Right, that's a great question, because it's another motivation for having this, having the two techniques, because this gives you a generating set description, right? Whereas the other one is an equation description.
Yes, it can be a way to decide the problem, but also to compute the generator.
Right, and this is, I mean, here for VAS, it's just polynomial time. For push down VAS, push down integer VAS. That's an interesting problem. If you can compute a generating set there, because there we only have the equation technique. That'd be interesting to look at, yeah.
Further questions? No, let's thank the speaker. So we have a coffee break.